For centuries, we have gazed into the night sky, listening to the stories told by the distant starlight. We built telescopes to see deeper, farther, and uncover the mysteries hidden within space. But the light is only part of the story. There is another subtle language that the universe speaks, a language of rings and echoes etched into the fabric of space and time. Welcome to the era of gravitational wave astronomy. Gravitational waves are a phenomenon in the fabric of space-time predicted by Albert Einstein a century ago. Unlike electromagnetic waves such as light, radio, or X-rays, which are oscillating electric and magnetic fields, gravitational waves are disturbances in the structure of space and time. They are created by the most powerful and energetic events in the universe. Einstein's theory of general relativity, published in 1915, proposed that large objects such as stars and planets do not exist in space. They bend it. This distortion is what we perceive as gravity. But Einstein left again. He proposed that when these massive objects accelerate, move, collide, or explode, they create holes in space-time. Like a stone thrown into a pond, ripples form on the surface of the water. Gravitational waves are caused by cataclysmic events, black hole collisions, supernova explosions, and neutron-star mergers. These waves travel through the universe at the speed of light, carrying with them information about the events they create. They tell us about the nature of gravity, the properties of black holes, and the birth of stars. But when gravitational waves reach us, they are incredibly weak, traveling billions of light-years across space. Their detection requires instruments of unprecedented sensitivity, machines capable of measuring changes over distances smaller than a fraction of a proton's width. This is a problem that has faced scientists for decades. In the 1990s, a new generation of scientists decided to build such a tool. The result was LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two large-scale detectors, one in Washington and the other in Louisiana, designed to detect this faint period. Their construction marked the beginning of a new era in the search for gravitational waves. Gravitational waves not only travel through space, they also travel through us. As these waves travel through the universe, they stretch and compress space, causing the distances between objects to change. But the question is, do gravitational waves stretch us too? In theory, yes. Gravitational waves stretch and compress everything, including us. However, the effect is remarkably small. A traveling gravitational wave would stretch you less than the width of an atomic nucleus. It is so small that it can never be felt. LIGO uses the world's most precise measuring device, the Laser Interferometer, to detect these minuscule changes. The device splits the laser beam and sends it into two perpendicular arms, each several kilometers long. When a gravitational wave passes through, it changes the length of these arms by small amounts, changing the way light is intercepted. This change indicates that the gravitational wave has passed. So, while gravitational waves do indeed stretch us, their effects are so minute that they can only be detected with the most advanced technology, such as the LIGO instruments. Through these ultra-precise measurements, we can hear the faint whispers of the universe. Gravitational waves are not only disturbances in space-time, they also carry energy. When massive objects like black holes merge, they release a lot of energy in the form of gravitational waves. This energy travels through space, traveling through space-time, and unleashing the most powerful events in the universe. The first detection by LIGO in 2015 confirmed that these waves remove energy from the source, causing the black holes to collide and eventually merge. The amount of energy these waves carry is astounding. In a fraction of a second, the merging black holes released more energy than all the stars in the observable universe. This discovery not only confirmed Einstein's theory, but opened a new way to understand the most energetic processes in the universe, revealing information about the objects and events that create these waves. Each detection tells a story about the formation and evolution of black holes, neutron stars, and even entire galaxies. Gravitational waves carry more energy than space. It allows us to see the most extreme environments of the universe, understand how black holes and neutron stars form, and study the nature of space and time. Gravitational waves have a profound effect not only on the space through which they travel, but also on the objects that create them. When two massive objects, such as black holes, merge, the gravitational waves they emit carry large amounts of energy. This loss of energy directly affects the motion and structure of black holes. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only absorb energy, but also determine the final outcome of the collision, whether a new, massive neutron star is formed or stars collapse into a black hole. These waves provide information about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals of cosmic violence, revealing the forces at play, the incredible energies, and the ultimate fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme conditions imaginable. To detect gravitational waves, scientists needed to build an instrument unlike any other, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is based on the simple but powerful idea of using light to measure the smallest distortions in space. The principle of LIGO is simple in concept, but complex in execution. The powerful laser beam is split in two, sending the light from two long arms 4 kilometers long, and at the end of each arm's mirror to a central reflector that reflects the light, where the two beams recombine. In the absence of gravitational waves, the rays cancel each other out due to their finely calibrated paths. However, when a gravity wave passes through the Earth, it is stretched in one direction while it is compressed in a perpendicular direction. This changes the length of the arms, changes the return time of the laser beam, and creates a unique interference pattern that LIGO's detectors can measure. To detect these incredibly small changes, LIGO must operate under extreme conditions. The entire interferometer is housed in an ultra-high vacuum tube to eliminate air molecules that can scatter the laser beam. The mirrors are suspended by finely tuned systems that isolate them from ground vibrations caused by traffic, wind, or even distant earthquakes. LIGO is not alone in detecting gravitational waves. A network of observatories across the globe work together to listen to the universe, combining their data to improve detection and accuracy. Virgo, located near Pisa, Italy, is LIGO's European counterpart. With its 3-kilometer-long arms, Virgo uses the principles of laser interferometry to detect gravitational waves. Partnering with LIGO, VIRGO helps pinpoint the location of cosmic events, allowing astronomers to point their telescopes to the right side of the sky in time. The CAGRA Observatory in Japan is bringing new innovations to this field. Located deep underground to avoid surface noise, CAGRA uses cryogenically cooled mirrors to reduce thermal vibrations, making it more sensitive to gravitational waves. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater precision. When a gravitational wave passes through the Earth, it arrives at each observatory at a slightly different time. By measuring these time differences, we can pinpoint the source of the sky waves. The global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed along with light, radio waves, and gamma rays. Together, they provide a more complete picture of the most extreme cosmic events. Gravitational wave astronomy is a truly global force. Scientists from all over the world work together to unravel the mysteries of the universe, proving that collaboration in science knows no bounds. Gravitational waves come in a wide range of frequencies, and each frequency reveals a different story about the universe. LIGO and its partner observatories are tuned to capture specific frequencies that correspond to the most energetic events in space. LIGO is designed to detect gravitational waves in the frequency range of about 10 Hz to 10,000 Hz. This range is well suited to pick up waves produced by events such as stellar mass black hole mergers or neutron-star collisions. These frequencies fall into a range similar to human hearing, but instead of sound waves traveling through air, they travel through space-time. Each gravitational wave signal can tell us about the things that created it. For example, the merger of two black holes roars. The wave pattern increases in frequency and amplitude, and as the black holes approach each other, they suddenly merge into a peak. The unique signature of each outburst allows scientists to determine the masses, orbits, and distances of the merging objects. However, not all gravitational waves are within LIGO's detection range. Low-frequency waves, such as those caused by the merging of supermassive black holes found at the centers of galaxies, are beyond LIGO's current capabilities. Detecting these low-frequency waves requires different instruments. This is where the future of gravitational wave astronomy comes into play. The planned Laser Interferometer Space Antenna, or LISA, will be deployed in space to detect these low-frequency gravitational waves. By extending our observing range, LISA will allow us to hear those deep, slow sounds of supermassive black hole mergers and other cosmic phenomena, further expanding our understanding of the universe. By expanding the range of detectable frequencies, we will open new windows into the universe, allowing for discoveries from the high-pitched squeals of merging neutron stars to the low-frequency hums of supermassive black holes. Each new frequency band brings new possibilities for understanding space. Astronomy broke ground in August 2017. For the first time in history, an astronomical event has been observed in both gravitational waves and electromagnetic radiation. The event, known as GW 170817, marked the dawn of many heralded astronomy. GW 170817 was the merger of two neutron stars, the remnants of massive stars that had previously exploded as supernovae. As these neutron stars orbited together, they emitted gravitational waves that were detected by LIGO and Virgo, and 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope observed the gamma rays that marked the event in the sky. This unique observation sparked an unprecedented global effort. Within hours, dozens of telescopes on the planet began observing the region at different wavelengths, from radio to X-rays, allowing scientists to study the event in more detail. The first joint observation provided important information about the workings of the universe. This proved that the fusion of neutron stars is the main platform for the production of heavy elements, such as gold and platinum, and their distribution into space. It was a long-suspected theory that has now been confirmed by direct evidence from gravitational waves. The discovery of GW 170817 demonstrated the tremendous power of combining gravitational wave and electromagnetic observations, allowing us to witness cosmic events with greater clarity and precision. It's a new window into the universe, where each discovery tells a deeper and richer story. Multimessenger astronomy heralds a new era of discovery, where light and gravitational waves work together to illuminate the deepest mysteries of space. Gravitational wave astronomy is still in its infancy, but its potential is enormous. What can we uncover in the coming years and decades? What new mysteries of space can we solve? With more sensitive detectors and more powerful instruments, we could soon find gravitational waves from sources we've never seen before. Could we be hearing faint echoes of the Big Bang, supporting theories about the earliest moments of the universe? Detecting these waves could provide direct evidence of cosmic inflation, the rapid expansion of the universe moments after the Big Bang. It could answer questions about the fundamental forces that shape the universe. Gravitational wave astronomy is the study of unknown phenomena, objects or events that we cannot even imagine. Exotic forms of matter, hidden dimensions, or mysterious dark matter that makes up most of the mass of the universe. Gravitational waves may help unravel these mysteries. We stand on the edge of discovery, poised to answer some of the deepest questions ever asked about our universe. Gravitational wave astronomy offers a new way to study space, opening the door to discoveries beyond our wildest dreams. The universe is full of whispers, and we have begun to listen. There is a phenomenon in the field of astronomy that has intrigued and puzzled scientists for years. Hidden behind the Milky Way's shimmering veil, in a region of space we call the escape zone. A gravitational anomaly so vast and so powerful that it touches the very fabric of our universe. It's a great puller. Although invisible to our telescopes, its gravitational influence is so strong that it affects the motion of galaxies hundreds of millions of light-years away, including our own Milky Way. But what's the big draw? Is it a supermassive black hole, a dense cluster of galaxies, or something else entirely? More importantly, what does its existence mean for us, our galaxy, and the future of the universe? In this video, we will explore these questions. The impact of the great attractor on our galaxy, and the challenges scientists face in observing this remote region of space. We will also travel to the recently discovered South Pole Wall, a large cluster of galaxies that stretches at least 700 million light-years into space and has an interesting connection with the Great Attractor. So, will we eventually end up with this anomaly, or does it still serve a different purpose in the grand scheme of the universe? Let's find out. 4 decades ago, astronomers used the Parkes telescope to observe the dust of the Milky Way. They discovered that our galaxy is traveling through space faster than expected. Imagine that our Milky Way travels through space at 2,500 times the cruise speed of an airplane, 55 times the escape velocity of Earth, and even more than twice the escape velocity of the galaxy. But where does such a movement come from? Here's the secret. The Big Bang theory of our origin states that every point in the universe must be different from every other point. However, the galaxies on either side of us should be moving at the same recessional speed, which should not result in a net motion in the Milky Way reference. A net motion can arise from nearby clusters in the distribution of matter, such as a large cluster of galaxies. The extra gravitational pull of such a cluster of galaxies could slow down and even reverse the expansion of the nearby universe. But no such cluster is visible in the direction of motion of the Milky Way. There is an excess of galaxies in the general vicinity and an excess of radiation in X-ray telescopes, but nothing large enough to explain the results. What are we observing? Superdensity of pure dark matter? Or is the theory of origin of mass and motion correct? Alan Dressler, an astronomer at the Carnegie Institution, used the first explanation, calling the lost concentration of matter the Great Attractor. But the mystery of the Great Gravitation continues to amaze us. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new filaments in the cosmic web, we have been unable to find anything to explain our motion. The Great Gravitation remains a mystery, tugging at our Milky Way and leaving more questions than answers. So, about 220 million light-years away, there is a gravitational anomaly known as the Great Dipper. Located within the Laniakea supergroup, this region of space has such a large gravitational field that it affects the motion of galaxies across hundreds of millions of light-years, including our own Milky Way. But what is the big draw? The term supercharger is coined to describe its gravitational influence. But it is not actually a single unit, but rather a region of space with a large concentration of mass. This mass consists not only of visible matter, such as stars and galaxies, but also of dark matter, invisible and mysterious matter, and according to some estimates, is about 85% of the mass of the universe. Understanding the Great Attractor is like putting together a cosmic puzzle. We know it exists because we can observe its gravitational effects, but we cannot see it directly because it is located in the exclusion zone, a region of space hidden by the Milky Way's dust and stars. Despite these difficulties, scientists have made great progress in studying the Great Attractor. They used a variety of techniques, including X-ray, infrared, and radio observations, to look at the Milky Way's dust and gas to understand this mysterious region of space. Part of a larger structure known as the Large Gravitational Norm Cluster, it is one of the most saturated galaxy clusters known to date. It is in this cluster that the center of the Great Attractor is located. The Norma cluster is moving toward the Big Dipper at a speed of about 1,340 miles per second. Thus, as we have seen, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light-years. In this region, known to us as the gravitational well of the Great Attractor, we have our own local group of galaxies, which are being pulled into the Great Attractor at a speed of about 370 miles per second. It's not easy to track down a Great Attractor. You can't just point a telescope at him. The main problem is its location. The Great Attractor is located behind the Milky Way, in a region known to astronomers as the escape zone. The zone is filled with dust and stars, making direct observations of the great gravitation difficult. But it did not stop astronomers from trying to reveal its secrets. They have to be creative in their methods, using different observations to examine the dust and gas of their galaxy. One of the main methods used is to observe a line of neutral hydrogen 21 centimeters long. This faint line can be detected by sensitive radio receivers, allowing astronomers to spot thousands of galaxies in blind surveys. The advantage of using radio waves is that they pass through the dust layer in the Milky Way, making our galaxy invisible. In the late 1990s, a group of astronomers began using the park's multi-point receiver, an innovative instrument located in New South Wales. This receiver's unique sensitivity and field of view enabled increasingly sensitive radio surveys of the sky. These studies, combined with new infrared data from the Hubble Space Telescope, allowed astronomers to confirm that 80% of galaxies found in the escape zone are located in the escape zone. The remaining 20% are too deep in the Milky Way to be detectable with existing optical or infrared telescopes. The escape zone is an interesting region of space. It is like a veil that hides part of the universe from our view. But with the help of advanced technology and innovative techniques, we could look behind this curtain and see the hidden galaxies. The use of infrared research has become very important. These studies allowed us to confirm the existence of previously hidden galaxies. It is like a torch that illuminates the dark corners of the universe. As space exploration and mapping continued, a massive structure known as the South Pole Wall was discovered across the vast expanse of space. This wall of galaxies, dust, and gas extends for at least 700 million light-years. It is so massive that it disrupts the local expansion of the universe. However, this large structure, like the Great Gravitation, is hidden behind our galaxy, the Milky Way. It stretches from the constellation Perseus in the northern hemisphere to the constellation Apis in the far south. But despite its proximity and size, it has long gone unnoticed, hidden in a dark sector of the southern sky. The South Pole Wall is a discovery recently announced by an international team of astronomers led by Daniel Pomerede of the Université de Paris and R. Brent Tully of the University of Hawaii. The discovery was made possible by measuring 18 million galaxies across 600 million light-years. Although the South Pole Wall is not visible to us, we can observe its gravitational effects. In the expanding universe, distant galaxies fly away from us. However, the galaxies between Earth and the South Pole Wall are moving away slightly faster than us, being pulled outward by the massive matter in the wall. In contrast, galaxies behind the wall move outward more slowly, being held back by the wall's gravitational resistance. The South Pole Wall is an important part of our local universe. It's as big as Sloane's Great Wall, but almost twice as big as us. But because of its hidden place in the southern part of the sky, it is still overlooked. It is connected to the larger structure of the Laniakea supergroup, which includes the Great Attractor. All of these structures are interconnected, affecting the local expansion of the universe and the motion of galaxies. The Great Attractor, the South Pole Wall, and other similar structures shed light on another cosmic mystery we're heading towards. Imagine that you are sailing down a river in a small boat. The current of the river, like the gravitational pull of these cosmic structures, drives your boat. No matter how hard you try to control your boat, current drag is so great that it ultimately determines your course and speed. Likewise, our galaxy is like a small boat on a cosmic river, swayed by the gravitational pull of massive structures like the South Pole Wall and the Big Dipper. In the future lies our understanding of the universe and the Great Gravitation. Australian astronomers are leading several pioneering projects. The Castro-initiated 2MTF study has made significant progress. Using the Park telescope, this survey calculates distances to galaxies and sheds light on the structure and motions in the nearby universe. But the research doesn't end there. An upcoming Wallaby study, due to begin later this year, promises to push the boundaries of our understanding even further. Using Australia's leading CSIRO-SKA Pathfinder, or ASCAP, telescope, this survey will allow us to probe deeper into the radio universe. Along with these radio surveys, the Australian Astronomical Observatory and ANU are launching a new optical survey called TIPAN. This project will focus on elliptical galaxies, allowing us to travel to distant regions of the universe. As research continues, our understanding of the universe is challenged. Theorists question the validity of the space-time metric currently used to describe the universe. There is talk of changing the general theory of relativity on a large scale. Looking out into space, we cannot imagine the future of the universe. What does the acceleration of the universe due to dark energy mean for us? For the Milky Way? For our Big Draw? For the countless galaxies that dot the cosmic landscape? The universe is not static. It is expanding, and this expansion is being accelerated by a mysterious force called dark energy. This force is so strong that it occasionally stretches the fabric, causing galaxies to drift apart. But what does this mean for the future of galaxies and superscales? What role does the Great Attractor play in this cosmic drama? Despite the expansion of the universe, the Great Gravitation continues to exert a gravitational influence on the surrounding galaxies, including our own Milky Way. So, back to the burning question: will the Great Gravitation swallow us up? The answer is no. Despite its massive gravitational pull, Gravity is not a space monster ready to swallow us whole. As the universe expands, its gravitational influence will weaken. In the distant future, as the expansion of the universe continues to accelerate, the galaxies currently attracted to the Great Attractor may drift apart. The gravitational bonds holding the superclusters together will weaken, and these large structures may begin to disintegrate. The future of the universe is a vast, expanding cosmic sea, with galaxies like islands in a cosmic ocean slowly receding from each other. The great gravitational force, once a formidable gravitational force, will eventually lose its grip on the galaxies around it.
Thanks to the rapid development of technology, astronomers are making more interesting and wonderful discoveries. For example, the title of the largest object in the universe changes from one discovery to another almost every year. Some of the discoveries are so large that they surprise you with their existence. In this issue, we will discuss a very unusual and incredibly large object called the Giant Gamma Ring, which is like a teleporter for the space fleet. The ring consists of 9 gamma-ray bursts spanning 5 billion light-years. What is it? How did it come about? We will try to answer these questions. Amazingly, the giant ring consists of 9 such gamma-ray bursts spanning 5 billion light-years. It's highly unlikely that this was any kind of accident, but we can't rule it out. The gamma-ray bursts that make up the newly discovered ring have been observed from space and from ground-based observatories. They are at a similar distance from us, about 7 billion light-years. 36 degrees across the sky, or more than 70 times the diameter of the full moon. This means that 20,000 gamma-ray bursts from a ring more than 5 billion light-years across are just one random occurrence in this distribution. Most current models show that the structure of space is uniform on large scales. Other recent results, and this new discovery, challenge the principle of establishing a theoretical limit of 1.2 billion light-years for the largest structures. If the ring is a true spatial structure, it should be almost visible to the eye. Gamma rays are rotated around the center of the object due to small changes in distance. This ring can be thought of as a spherical projection of these gamma-ray bursts, which occurred a long time ago, 250 million years ago. A short time compared to the age of the universe. So how can such a structure come about? Researchers consider 2 explanations for what the observed objects look like. In the simplest case, galaxies can lie in the same plane, thus forming a single ring. This means that it is oriented almost perpendicular to the direction of the observer's view of the Earth. Another explanation is that this structural plane is not a real object, but a projection of the sphere onto the celestial plane. Dots placed randomly on the sphere will cluster around the edge of the projection circle, creating the illusion of a ring. The existence of a cluster of this size may contradict cosmological principles about the uniformity of the universe. Previous studies with the Planck and WMAP instruments limited the size of the space object to 1.2 billion light-years. It is precisely this order of magnitude that would seriously undermine the notion of unity based on microwave observations. If the author's findings are confirmed, astronomers may have to reconsider the constraints on the evolution of the universe. The first example of such giant formations was the discovery of a quasar cluster in 1982. It was about 350 million light-years across. Later, however, larger but unstructured objects were discovered. Sloan's Great Wall, 1.37 billion light-years. Hercules' northern corona is more than 10 billion years old, about 10% of the observable universe. These flat formations consist of alternating cavities and clusters of galaxies. Who knows what we'll discover tomorrow? Yes, the universe never ceases to amaze. In 1950, the Dutch astrophysicist Jan Oort proposed that all comets form a cloud that orbits the inner part of the solar system. It is not uncommon to observe celestial objects around the Sun, where material around the hottest star evaporates and is carried away by cosmic winds. These paired celestial bodies are comets. Evidence that comets leave very distant parts of the solar system is their long orbits. Astronomers record the movement of about a dozen comets every year, but in reality, all these things appear in a distant cloud. The outer part of the solar system is believed to be surrounded by them. To find the answers, we suggest going on an amazing journey.
Solar system. The Sun's gravitational pull is limited relative to its neighboring stars, that is, between the Sun and the closest stars. Therefore, if the distance to the nearest stars is light years, the solar system is on the order of several light years. So the solar system is a very large unit, 1,000 times larger than the orbits of the most distant planets. And we have to wait tens of thousands of years for the traveling system to fly beyond the boundaries of the solar system. It would also be correct to say that the boundaries of the solar system are defined by the Oort cloud. To date, the estimated mass of the cloud is only 80 Earth masses of ejected material. Yes, it may not look like much, but the Oort cloud is actually a giant sphere of scattered material with an astonishing diameter. Some astronomers estimate that this region begins about 2,000 astronomical units from our star and ends at about 70,000 astronomical units. The Oort cloud is believed to be the grave of the planet. This reservoir of trillions of icy objects formed early in the formation of the solar system, when giant planets ejected smaller objects from its boundaries. From time to time, some of it turns towards the Sun and takes the form of a comet. The Oort cloud is hypothesized to include two distinct regions, a spherical outer Oort cloud and a disc-shaped inner Oort cloud. The stuff in the cloud is mostly made up of water, ammonia, and methane ice. It probably formed near the Sun and was dispersed into space by the gravitational effects of the giant planets early in the development of the solar system. Although there are no direct observations of the Oort cloud, astronomers believe it is the source of long-period and Galilean-type comets, as well as many Centaurs and Jupiter family comets. The outer part of the Oort cloud is the approximate boundary of the solar system, and can easily be affected by the gravitational pull of both passing stars and galaxies. These forces sometimes cause comets to drift toward the center of the solar system. Short-period comets, based on their orbits, can originate from the Oort cloud as well as from the diffuse disk. We mentioned that the value cloud contains a lot of material. But what does it represent? The outer Oort cloud is thought to contain several trillion cometary nuclei, more than 1.5 miles. The average distance between comets is several tens of millions of kilometers. Incidentally, Comet Gallia is a suitable prototype for all comets in the outer Oort cloud. The combined mass of all the large comets in the cloud is about 5 times that of Earth. The mass of the inner Oort cloud is currently unknown. Comet bodies can be trapped in the Oort cloud for a long time, ejected from the solar system, or escape into the Sun's orbit to become true comets. Comets aside, most Oort cloud objects are made up of various ices that contain substances such as water, methane, ethane, carbon dioxide, and cyanogen. However, the discovery of object 1996 PW, an asteroid with an orbit typical of long-period comets, suggests that the Oort cloud may contain rocky objects. Here is an example. Analysis of the ratio of carbon and nitrogen isotopes in the Oort cloud and Jupiter family comets shows only small differences, regardless of their individual regions. It is concluded that the objects of these regions were formed from the original protosolar cloud. This conclusion is also supported by studies of particle sizes in Oort cloud comets. It's also amazing how the gravitational effects of neighboring stars and galactic waves can change the orbit of money, making them more rounded. This explains the nearly spherical shape of the outer Oort cloud. This means that the Hills cloud, which is more tightly bound to the Sun, must eventually have a spherical shape. Recent studies have shown that the formation of the Oort cloud undoubtedly corresponds to the hypothesis that it formed as part of a star cluster of 200 to 400 stars. These larger, nearby stars likely played a role in the formation of the cloud, because the close paths of the stars within the cluster were much more frequent than today, and caused more frequent perturbations. The current position of many comets seen near the Sun is thought to be due to the gravitational disturbance of the Oort cloud, caused by tidal forces caused by the Milky Way galaxy. The tides rise and fall as the tidal forces of the Moon bend and distort the Earth's oceans. In the inner solar system, these effects are negligible compared to the Sun's gravity. However, in the outer solar system, the Sun's gravitational pull is weaker, and the gradient of the Milky Way plays a much more important role. Because of this gradient, galactic waves can disrupt the Oort spherical cloud, stretching the cloud toward the galactic center and compressing it along the other two axes. These weak galactic perturbations may be sufficient to move valuable cloud objects from their orbits toward the Sun. By the way, there are interesting calculations according to which, during the existence of a planetary system, extraterrestrial stars pass 10 times as far from the inner comet rim, making comets 1,000 times more frequent. Such an event has been going on for about 400,000 years. Up to 200 comets fall to Earth during this period, an average of one every 2,000 years. On the scale of a human lifetime, of course, this is not particularly noticeable, but on a geological scale, we can talk about a shower of money. They even tried to link such showers with extinction on our planet. In addition, information about the periodicity was explained by the presence of Nemesis, a dark star with a mass of a few hundredths of the Sun. Nemesis, according to this hypothesis, travels in a long orbit around the Sun and enters the money cloud every 26 million years. However, the Pioneer 10 station, outside the planetary system, did not experience any additional acceleration, which could be explained by the impact of Nemesis, or at least a large planet the size of Jupiter. The influence of 3 to 5 mass bodies cannot be ruled out, so the Oort cloud is a really interesting and mysterious region where there are tens of billions of money nuclei. Some of them we have already seen, others we have yet to see. We know that the minimum temperature is minus 273.15 degrees. Why? Because at that temperature, the movement of particles stops, and the heat energy they emit becomes zero. I wonder if there is a minimum temperature. Maybe there should be a maximum temperature. And logic dictates that the particle must reach a maximum at such a point that it cannot release any more heat energy. But is it really so? To understand, it is necessary to define what temperature is in general, and also trying to find the sources of the highest temperature in the universe. Let's try it out. All life, from bacteria to Krogan to reapers, can sense heat and cold directly through their senses. But given our lack of superpowers, our options are very limited. This is because this definition of temperature requires measuring temperature with instruments rather than by hand. Such instruments are called thermometers and measure the so-called empirical temperature. The empirical temperature scale defines the scale of measurement and the number of divisions between them. Here are the scales we use today, including Celsius, Fahrenheit, and more. But absolute temperature, measured in Kelvin, is entered with a single point, the point on which the measuring scale is based. Given that there is a minimum limiting value of temperature in nature, an absolute number, the upper value of the temperature is limited by the Planck temperature. This is a type of maximum temperature. The highest temperature was thought to be 10 trillion degrees. It is artificially obtained from the Earth. This absolute temperature record was obtained during an experiment at the Large Hadron Collider, the world's most powerful elementary particle gas pedal. At speeds close to the speed of light, particles collided with high-energy lead ions. When the heavy ions collided, many big explosions, dense regions of fire with such high temperatures, began to appear. At such temperatures in energy, the nuclei literally melt and form a pile of their quarks. The result was the highest temperature plasma in the laboratory. Although 10 trillion degrees is an incredibly high temperature, it seems far from the limit. As everything is limited within this experiment, technology does not allow us to go further. So I suggest going on a space trip in search of the hottest source in the universe. And we start with the closest planet, Venus. 90 characterized by an unusually dense atmosphere with a pressure equivalent to Earth's atmosphere. Due to the amazing greenhouse effect, the surface temperature of the planet reaches 480 degrees, which is more than Mercury. Many known objects can also approach the Sun at record distances. This includes the asteroid Phaedo, whose temperature can reach 750 degrees Celsius. But the object passes through the Moon Io at a temperature that has been one of the biggest surprises in the probe of the Peter system by space probes. Its surface is the youngest in the solar system and has no impact craters. Measurements from the Galileo space station show that the temperature of volcanoes on this satellite reaches at least 1,340 degrees Celsius. The surface of the Sun has a temperature of about 5,500 degrees Celsius. However, about 10,000 kilometers from the surface of the Sun, there is the solar corona, which we see as a type of halo. Its temperature reaches 1,000,000 degrees, but not only that. A solar flare can have temperatures of tens of millions of degrees. However, the Sun is an ordinary star in the universe. Surface temperatures of ordinary stars range from 2,000 degrees Celsius in red dwarfs to 30,000 degrees Celsius in blue dwarfs. But it should be remembered that there is a special class of stars. Stars known as Wolf stars can have surface temperatures in excess of 50,000 degrees Celsius. The number of known stars of this type in the local group of galaxies may be only a few thousand. Such stars are characterized by high-density, planetary crust-like debris shells. They are thought to represent the final stage of single large-scale stellar evolution before the supernova explosion phase. Their hottest star is believed to be WR102, with a temperature of 210,000 degrees Celsius, 500,000 times that of the Sun. This star has a mass of 20 solar masses and a radius of less than 0.4 solar radii. But stellar debris is even higher. For example, the discovery of the hottest white dwarf RxG0439 with a temperature of 240,000 Celsius was announced in 2015. We are approaching the exotic remnants of the stars. These are neutron stars that have even higher surface temperatures. Their maximum radiation is in the X-ray range and gamma rays. Thus, the brightest sources of gamma rays are the neutron stars in the Crab Nebula, the Sales Nebula, and the quiet radio star Geminga. When a neutron star is born, its surface temperature is estimated to be about 100 billion degrees Celsius. This is a high temperature but far from extreme. Finally, we reach black holes. In front of us, for example, is a black hole with a stellar mass of X1, the brightest X-ray source in the sky. Recent observations have shown that the effective temperature of the nearest quasar core is 30,273.40 trillion degrees. The effective temperature of dark matter in active galactic nuclei is about zeta Kelvin, tens of millions of times the observed temperature of matter seen in these objects. The universe is hiding even hotter things, but we can't reach them yet. And yet, we understand that the highest temperature was during the Big Bang, or when inflation began. The theory says that the temperature of our universe was equal to the Planck temperature. Modern physics believes that this point is the highest, and that it is not 10 trillion degrees, but much higher. In the new theory, the limiting temperature should be 142 centillion. Yes, as you can see, this figure is much higher than our Earth experiment. But why is there such a difference? The thing is, there is such a thing as a state, and there is such a thing as a particle's velocity distribution. The concept of temperature for the former system state is not defined at all. The temperature is strictly defined for one species, a state of equilibrium called Maxwell's velocity distribution. This probability distribution, found in physics and chemistry, is at the heart of the kinetic theory of gases, which explains many fundamental properties of gases that are not accounted for experimentally, including pressure and diffusion. From this, we can conclude that there seems to be no theoretical absolute maximum temperature, as the system can be heated to any desired temperature. Another question is what processes will occur at high temperatures and whether we can describe them. This is because at extreme temperatures, molecules begin to dissociate into atoms first. Then atoms begin to decay into nuclei and electrons, then nuclei into nuclei, and then nucleons into a quark-gluon plasma, the fundamental particles that make up quarks, protons, and neutrons. But what comes next is unclear. Quarks are elementary particles that have nothing to decay into. What happens at high temperatures, pressures, and superspeeds? It is not clear at all. So the maximum limit should work in this case. We don't know what will happen at extreme temperatures. So the question obviously remains open. No light is visible. Invisibility is one of his most recognizable traits. We only see it when it hits our retina. Yes, we cannot see light that just passes through without reflecting anything. Imagine an empty, dust-free, completely sterile room. Before the end of the experiment, the light must not have time to reach the walls, or the walls of the room must be black to completely absorb the light. Now imagine the lantern there from the outside. That's great! You cannot see the lantern, not the lantern itself, but the light it gives off. Paradoxically, light is invisible. We can't see it up close unless it's reflected off of something. If there was something reflecting the light, even dust or water droplets, to scatter the light, we would be able to see it. But since there is nothing in the beam, and we are looking at it from the outside, his light does not reach us. If there was a second light source in the room, we could see the flashlight, but not the light it emitted. Rays of light, no matter how powerful we can get them even with a laser, pass each other as if there was nothing in their way. These considerations are included in the book The Structure of Reality by British physicist and philosopher David Deutsch, one of the founders of the concept of quantum computing. The book as a whole makes it clear that the age of grand philosophical systems is not a thing of the past. The author provides a coherent answer to one of the most fundamental philosophical questions. What is the essence of reality? Today we try and figure it out. As you move toward the observer in the reflector and back from the flashlight, the reflector will appear even smaller and even worse when only a point is visible. The question arises, is light really able to propagate infinitely in the finest rays? The answer is no. At a distance of about 10,000 kilometers from the lantern, its light would be too faint for the human eye to perceive, and an observer would see nothing. Therefore, man would see nothing but a more sensitive seeing animal. Take the frog, for example. His eyes are several times more sensitive than human eyes. This is enough to make a noticeable difference in the experiment. If the watcher were a physical frog, and he moved away from the flashlight, there would never be a moment when he lost it completely. Instead, the frog would see the flashlight begin to glow. The flashes occur at uneven intervals and will increase as the frog moves away from the flashlight. But the individual lights would not be brighter. Already 100 million kilometers from the flashlight, The frog would see only one flash per day on average, but this flash would be no less than any other flash observed at a different distance. Unfortunately, we do not know the language of frogs, which means that there will be no scientific debates with them. That is why researchers use photomultiplier tubes in real experiments. These are more sensitive light detectors than frog eyes, and reduces light through dark filters. Observing light 100 million miles from the source is somewhat problematic. However, neither the principle nor the result changes. Imperceptible darkness, uniform darkness, glare, and even brightness, no matter how dark we use the filter. This flash proves that there is a limit to the uniform distribution of light. Each flash is caused by a photon hitting the retina. Light rays are weakened not because the photons themselves are weakened, but because they are separated from each other, and the space between them increases so the light hits the retina. This property of light only occurs in discrete quantities and is called quantization, and a single piece of light, a photon, is called a quantum. Quantum theory, by the way, gets its name from this property that is attributed to all measurable physical quantities. Yes, everything that surrounds us and seems to be continuous is not. There are many different phenomena in quantum physics. Quantization is the simplest. Let's get back to our photons. You've heard many times about Thomas Young's 2.5 experiment. This experiment belongs to the general class of dual-path experiments, in which the original wave is split into two separate waves, which are then combined into one. Changing the path length of the two waves results in a phase shift, creating an interference pattern. Young's experience is the fallacy of theories that treat light only as a stream of particles. If the photons exhibited only corpuscular properties, the screen would show two brightly lit areas behind the light and a dark area between them. Young's experience forced physicists to consider the wave properties of light, meaning that each real photon must be at least 1 trillion shades of green. But interference is not limited to photons. Quantum theory is perturbed by any particle. Therefore, every real neutron must be accompanied by shadow neutrons, each electron, shadow electron mass, etc. This means that reality is much larger than it appears, and most of it is invisible, and the objects and events that we can observe with instruments are only the tip of the iceberg.
The observable universe is home to truly astonishing large-scale structures that represent the breadth and depth of cosmic architecture. Among these giants are galaxy superclusters, large groups of galaxies that are gravitationally bound together. One of the most prominent superclusters is the Laniakea supercluster, which serves as our cosmic neighborhood. It contains approximately 100,000 galaxies and spans over 150 million light-years, representing the mind-boggling scale involved in our universe. In addition to superclusters, there are even larger formations known as cosmic filaments. These filaments consist of galaxies and dark matter, weaving complex patterns into the large-scale structure of the universe. The Sloan Great Wall is an important example of a cosmic filament, more than 100 million light-years long. Such large structures are interconnected to form a vast web architecture with empty spaces between them. This suggests that galaxies are not evenly distributed throughout the universe, but rather they form a complex region under the influence of gravity and dark matter. Even more impressive are the largest structures ever discovered, such as the Great Wall of Hercules Corona Borealis. This massive supercluster measures about 10 billion light-years across and is considered the most well-known structure in the observable universe. Its discovery complicates our understanding of cosmic evolution because it raises questions about how such large regions come together and what forces govern them. These massive structures provide important insights not only into the vast scale of space, but also into the fundamental processes that shape the universe over billions of years. As scientists continue to study them, they learn more about the basic fabric of matter, energy, and nature. The pursuit of knowledge about these great clusters piques our interest and our desire to understand our place in this grand cosmic scheme. Galaxy filaments and cosmic networks are the result of gravitational interactions and the complex dynamics of dark matter in the universe. These structures appeared in the early stages of cosmic evolution after the Big Bang. As the universe cooled, matter began to clump together under the influence of gravity. Dark matter plays a key role in this process. It does not interact with light, making it invisible, but its gravitational pull has a significant effect on the distribution of galaxies. Over billions of years, regions with a slightly higher density of core matter began to attract more matter, forming the seeds of galaxies and clusters. As these local gravity wells deepened, they attracted more and more material from their surroundings. This created filaments, which are long structures that look like spaceships. These filaments connect large clusters of galaxies and form the web structure that fills the universe. As the universe continues to expand, the dynamics of matter evolves. Galaxies within the filaments are attracted to each other, eventually forming clusters at their intersections. This gravitational hierarchy is surrounded by high-density large voids that contain relatively few galaxies. The interplay of filaments provides the foundation upon which the universe is structured, displaying a beautifully orchestrated spatial arrangement. Computer simulations and observational data from telescopes are further enhancing our understanding of this phenomenon. These simulations show how dark matter affects the evolution of cosmic structure. Large-scale surveys, such as the Sloan Digital Sky Survey, allow astronomers to detect and map these large filaments, confirming theoretical models. Together, they reveal the dynamic processes that create the elegant cosmic web that spans our universe. Cosmic voids are the vast, empty spaces between galaxies and galaxy clusters that represent some of the larger structures in the universe. These voids can be tens to hundreds of millions of light-years across and are characterized by a lack of matter compared to denser regions. Although they appear to be devoid of galaxies, a closer inspection reveals that they are not entirely empty. They often contain faint galaxies, dark matter, and diffuse gas, albeit in much lower concentrations than their denser counterparts. The existence of these cosmic voids provides insight into the overall structure of the universe. The proliferation of voids and their surrounding filaments and clusters represent the web-like architecture of the universe, a phenomenon that reflects the influence of gravity over billions of years. Gaps are crucial to understanding cosmological evolution because they help scientists investigate the origin and nature of cosmic structure. By studying the vacuum, researchers can understand the changes in density that occurred in the early universe. Moreover, the properties of cosmic voids challenge our understanding of dark energy, the mysterious force that causes the universe to accelerate. The behavior of matter in and around voids can reveal valuable information about how dark energy affects the expansion of space. For example, observing how galaxies move in and around voids can provide information about the distribution of mass in the universe and help us understand cosmic dynamics. The study of cosmic voids also raises interesting questions about the fundamental nature of the universe. They serve as testing grounds for cosmological models, allowing researchers to assess the validity of theories such as the Standard Model of cosmology. As science advances and observational techniques improve, space probes continue to unravel the mysteries of the universe, enhancing our understanding of the governorship of cosmic evolution. Dark matter plays an important role in the formation and evolution of cosmic structures throughout the universe. Although invisible, neither emitting nor absorbing light, dark matter makes up about 27% of the total mass-energy content of the universe. Its gravitational influence is key to understanding how galaxies, clusters, and even larger structures such as superclusters and cosmic filaments are formed and maintained. In the early universe, after the Big Bang, matter began to clump together under the force of gravity. Although the normal matter that emits light and forms stars and galaxies begins to accumulate, It is dark matter that does not appear to form the basis of this cluster. Dark matter does not interact electromagnetically, meaning it does not collide with matter to dissipate energy. This property allows it to remain gravitationally bound and form massive halos surrounding galaxies and clusters. These halos act as gravitational wells, attracting ordinary matter and helping the formation of stars, galaxies, and larger structures. The processes of cosmic evolution and structure formation are closely related to the behavior of dark matter. When galaxies merge or interact, their dark matter can also collide and merge, which can lead to the growth of large galaxies and galaxy clusters. Understanding the dynamics of dark matter interactions helps scientists explain phenomena such as the rotation curves of galaxies. These curves show that stars orbiting outside galaxies are moving faster than expected based on visible matter. This suggests that there is additional invisible mass associated with dark matter. Astronomical observations and simulations of large-scale structures shed more light on the role of dark matter. By mapping the distribution of galaxies and clusters, researchers can map the corresponding distribution of dark matter. Projects such as gravitational lensing provide direct evidence of the existence and distribution of dark matter throughout the universe by measuring how light from distant objects is bent by massive structures. As researchers continue to explore the nature of dark matter, they enhance our understanding of its profound effects on the cosmic landscape and the structure of our universe. Beyond our observable universe lies a tantalizing and enigmatic realm. Although we can analyze the structures in the cosmic environment, understanding the nature of these cosmic structures is influenced by many different cosmological theories. One common idea is that the conditions surrounding these structures may vary, resulting in different formations. For example, while our universe exhibits a specific distribution of galaxies, clusters, and voids, other regions may vary in density and order, resulting in different large-scale structures. One hypothesis suggests that physical laws may differ in different regions of the universe. If fundamental constants such as gravity or the speed of light differ from our observable horizon, the evolution of cosmic structures in these regions may produce results that differ dramatically from what we witness nearby. Such changes could lead to exotic astrophysical entities or entirely new celestial shapes that defy our current understanding of physics. In addition to potential changes in physical laws, the overall geometry of spacetime is a critical factor influencing the structure of the universe. Measurements of the cosmic microwave background radiation suggest that the observable universe appears to be flat. However, if the universe is truly infinite and far beyond what we can observe, it could introduce various curvature features that could affect the development of large-scale cosmic structures. The concept of the multiverse also comes into play, where our universe is potentially one of countless others, each with its own unique physical properties and structural formation processes. In such a scenario, some universes may adopt strange structures or even strange rules governing their cosmic evolution. While these ideas remain speculative, they drive the imaginations of scientists and theorists, furthering the exploration of the mysteries of the universe. Attempting to understand these hypothetical cosmic realms beyond the visible universe deepens our uncertainty. Dark matter is a mysterious, non-luminous component of the universe that does not emit, absorb, or reflect light, making it invisible to conventional observational techniques. Dark matter is thought to make up about 27% of the mass energy of the universe. Scientists estimate its existence based on its effects on visible matter, radiation, and the overall structure of the universe. One of the strongest lines of evidence for dark matter comes from observations of galaxy rotation curves. When astronomers measure the speed of stars orbiting in the outer regions of galaxies, these stars move much faster than expected based on the gravitational effects of visible matter such as stars and gas. According to Newtonian physics, they should show a decreasing velocity as they move away from the galactic center. However, the observed velocity remains constant, indicating that the galactic halo contains more mass than can be accounted for by stars and gas alone, possibly in the form of dark matter. Another important piece of evidence comes from gravitational lensing, the phenomenon in which light from distant galaxies is bent by the gravitational pull of large foregrounds such as galaxy clusters. Observations show that the amount of bending goes beyond that which depends only on the apparent mass. This inconsistency suggests that there is additional invisible mass that exhibits gravitational pull, consistent with the presence of dark matter. Moreover, the distribution of galaxies in the universe follows a web structure under the influence of dark matter. Cosmic structure formation simulations involving dark matter agree closely with observations of the large-scale structure of the universe, such as galaxy clusters and voids. These models suggest that dark matter acts as clusters of visible matter that guide the formation of galaxies and other cosmic structures. The exact nature of dark matter remains a deep mystery, and various candidates have been proposed, such as non-massive particles. Research is ongoing, using cutting-edge technologies and experiments aimed at directly or indirectly detecting dark matter. The search for dark matter is important because it not only holds the key to understanding the composition of the universe, but also informs the fundamental laws that govern the cosmos. Dark matter has a profound effect on galaxy formation and the overall architecture of the universe. Its gravitational properties are important in shaping the large-scale structure we observe in the universe today. In the early universe, shortly after the Big Bang, dark matter began to clump together, forming massive halos that provided a gravitational field within which ordinary matter could gather. This high concentration of dark matter created gravity wells that attracted gas, dust, and other simple matter, facilitating the birth of galaxies. As galaxies form, their dark matter plays an important role in determining their size, mass, and rotation speed. Dark matter helps maintain the stability of galaxies by providing additional gravitational pull only with visible matter. This stability is particularly important because the forces at play during galaxy formation are enormous, and the gravitational pull of dark matter allows complex structures to form that do not collapse under their own dynamics. When galaxies interact or merge, the dynamics of their dark matter has a significant impact on the outcome of these events. For example, during a merger between two galaxies, their dark matter halos can collide and merge with visible matter. This interaction can lead to the formation of larger galaxies, which often exhibit different properties compared to smaller ones. This merger process is a critical aspect of galaxy evolution, contributing to the development of cosmic structures throughout the universe. On a larger scale, dark matter represents the overall distribution and motion of galaxies. The gravitational influence of dark matter creates the structure of the cosmic web, where galaxies and clusters form along filaments and nodes with large gaps between them. This gravitational network shows how dark matter organizes space and affects the motion of galaxies over time, shaping the dynamic behavior of galaxies and clusters as they move through the evolving universe. Dark matter is more than just a facilitator of cosmic evolution. It serves as the primary force driving the formation and construction of galaxies and the larger cosmos. The search for dark matter particles has led scientists to propose several interesting candidates, each from a different theoretical background in particle physics and cosmology. One of the most widely studied candidates is the weakly interacting massive particle, often abbreviated as WIMP. WIMPs are predicted to have masses on the order of hundreds of GeV or giga-electron volts and interact with the weak nuclear force and gravity. The theory postulates that they were produced in large quantities in the early moments after the Big Bang. Direct detection of WIMPs will be difficult due to their weak interactions, but some experiments aim to observe scattering events with potential matter. Another promising category of dark matter candidates is the hypothetical elementary particle proposed to solve problems related to quantum chromodynamics. Particles are light, slow-moving particles that can make up a large portion of dark matter. They will interact very weakly with other particles, effectively repelling them. Researchers are exploring the potential for detecting axons through experiments that look for them to convert into photons when exposed to strong magnetic fields. There are also supersymmetric particles, which arise from theories that extend the standard model of particle physics. In these models, each elementary particle has different properties. Candidates from supersymmetry, such as neutralinos, have the necessary properties to account for dark matter. Their stability and interactions governed by the weak force make them strong candidates in some theoretical frameworks. Finally, supermassive black holes provide an alternative explanation for dark matter. These would arise from changes in density in the larger universe, potentially accounting for the effects of dark matter through gravitational interactions. Although this theory differs from ordinary particle candidates, it remains a point of active research given the complexity of cosmological evolution. These candidates bring together the various approaches taken to solve the dark matter enigma. Ongoing experiments are designed to detect or rule out these possibilities, improving our understanding not only of dark matter, but of the fundamental physics of the universe. Each approach promises to advance scientific knowledge and may lead to profound discoveries about the composition of the universe and the laws that govern it. Dark energy is an enigmatic form of energy that permeates all of space and is responsible for the observed acceleration of the universe. Dark energy, which accounts for about 73% of the total mass energy content of the universe, has puzzled scientists since its discovery. Unlike ordinary matter and dark matter, which are gravitationally attracted, dark energy exerts a repulsive force, causing galaxies to accelerate apart from each other. Traces of dark energy were first discovered in the late 20th century, primarily through observations of distant supernovae. In the mid-1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the luminosity of JA supernovae, which serve as a reliable standard candle for determining cosmic distances. By observing these supernovae, teams would discover that the universe's expansion is slowing due to gravity. However, their data showed a surprising result. The supernova appeared darker than expected, indicating that they were farther away than previously thought. This led researchers to conclude that the expansion of the universe is accelerating rather than slowing down. The key to understanding this acceleration lies in the concept of dark energy. To explain the observations, scientists introduced dark energy as the driving force behind the accelerated expansion. Various theoretical frameworks have been proposed to describe dark energy, one of the most famous models of the cosmological constant. The cosmological constant, proposed by Albert Einstein at the beginning of the 20th century, simultaneously complements the energy density. This reflects the idea that as the universe expands, the energy density remains constant. Other theories have emerged, including quintessence, which suggests that the density of dark energy may change over time. Despite these various models, the true nature of dark energy remains elusive. Observations of the cosmic microwave background, the large-scale structure of the universe, and other astrophysical phenomena have helped improve our understanding of dark energy. Ongoing research continues to investigate this mysterious substance, as unraveling its nature could shed light on fundamental aspects of the universe and the ultimate fate of cosmic evolution. Dark energy plays an important role in the future of the universe, primarily because of its role in the accelerated expansion observed over the past few billion years. As dark energy continues to exert its influence, it shapes potential scenarios for the ultimate fate of the universe. The exact nature of dark energy remains an open question, but its consistency suggests several futures for the universe. Big Freeze Scenario. In this model, as the universe expands at a rate controlled by dark energy, galaxies gradually fade away from our observable horizon. Over large timescales, star formation will slow down, leading to an increasingly cold and dark growing universe. Existing stars will run out of nuclear fuel, and without new stars forming, most of the matter will remain in the form of black holes and white dwarfs. Eventually, the universe will reach a state of thermodynamic equilibrium, characterized by a uniform temperature near absolute zero, rendering it a desert and inert space. Another scenario is a big rip, where the influence of dark energy increases, causing the escape to expand. In this model, the accelerated expansion can be so pronounced that it eventually separates galaxies, stars, and even atoms. If the energy density of dark energy increases without limit, all large-scale structures will collapse, ultimately leading to a catastrophic end to the universe. At the other end of the spectrum, some theories suggest that dark energy could evolve over time, perhaps leading to a steady state or even transitioning to gravitational forces. This change could reverse the current acceleration of cosmic expansion, allowing galaxies to merge and form larger structures, leading to a cyclical pattern of cosmic evolution. As researchers gather more information from observations of supernovae, the cosmic microwave background radiation, and galactic scattering, they aim to improve our understanding of dark energy and its effects on the universe. Each of these potential destinies points to the complex relationship between dark energy and the cosmos, revealing how this mysterious force can ultimately shape evolution and the fate of everything within it. The evidence for the expansion of the universe is strong and multifaceted, contributing to our understanding of cosmological dynamics. One of the earliest and most compelling evidences comes from observations of galaxies and their redshifts, recognized by Edwin Hubble in the late 1920s. Hubble noted that distant galaxies are moving away from us, and the light they emit shows a shift to the red end of the spectrum. This red shift indicates that the wavelengths of light are stretched as galaxies shrink, a phenomenon consistent with the Doppler effect. Hubble formulated his law, which states that the farther away a galaxy is, the faster it is moving away and the universe is expanding. In addition, the cosmic microwave background rays, the glow left over from the Big Bang, provide further support for this expansion. Discovered in the 1960s, this relic radiation is remarkably uniform, but there are small variations that reveal information about the density and temperature of the universe. Measurements from satellites, such as the Wilkinson Microwave Anisotropic Probe and the Planck mission, show these changes with great precision. According to the data, the universe has been expanding since its creation, and the cosmic microwave background serves as a snapshot of the universe as it was around 300,000 years ago, after it cooled enough to form atoms. Supernovae also contribute to the evidence for the universal expansion, particularly type Ia supernovae, which serve as reliable standard candles for measuring astronomical distances. Observations at the end of the 20th century showed that these supernovae were less luminous than expected, suggesting that they were far away due to the acceleration of the universe's expansion. This discovery was instrumental in proving not only the expansion of the universe, but the expansion rate is increasing due to dark energy. Finally, the large-scale structure of the universe, including the distribution of galaxies and cosmic filaments, provides additional evidence for expansion. Current observations show that galaxies are not uniformly distributed. Instead, they form a large cosmic web structure that interacts with gravity. This distribution is a direct result of the expansion history of the universe, further reinforcing the paradigm of a dynamically evolving cosmos under the influence of forces at play since the Big Bang. Together, this evidence creates a powerful picture of an ever-expanding universe, with each piece contributing to our understanding of its origins and evolution over time. The Hubble constant is a key parameter that describes the rate at which the universe is expanding. It shows the relationship between a galaxy's distance and its rate of recession, providing a measure of how quickly galaxies are moving away from us as the universe expands. The Hubble constant is usually expressed in megaparsecs per kilometer per second, meaning that for every additional megaparsec, the galaxy is receding by a certain number per second. Edwin Hubble's discovery of this relationship in the late 1920s fundamentally changed our understanding of the universe. His observations showed that galaxies farther from Earth are receding at a greater rate, indicating that the universe itself is expanding in one direction. This expansion can be thought of as the stretching of space, with the galaxies embedded in that space dissipating over time. Understanding the Hubble constant is critical to determining the size and age of the universe. By measuring the recession velocities of different galaxies and their distances using methods such as standard candlestick or redshift measurements, astronomers can calculate the Hubble constant. This measurement allows scientists to estimate how long the universe has been expanding since the Big Bang, yielding its age, which is currently about 13.8 billion years. However, it should be noted that measurements of the Hubble constant yielded slightly different values depending on the methods used. Planck satellite observations measuring the cosmic microwave background radiation suggest a certain value for the Hubble constant, while measurements from large surveys of supernovae and galaxy distributions provide larger values. This discrepancy has led to debate and research in the field of cosmology, as scientists seek to reconcile these differences and better understand the underlying physics of the universe's expansion. Ultimately, Hubble serves as an important bridge connecting observations of constant recession velocities and distances, strengthening its role in understanding the expanding universe and guiding future investigations into its fate. Cosmic acceleration refers to the observed expansion of the universe over the past few billion years. This continuum behavior indicates that the galaxies are moving away from each other at increasing speeds rather than slowing down, as would be expected from gravitational acceleration. The discovery of cosmic acceleration changed our understanding of the dynamics of the universe and had important implications for cosmology. The main explanation for cosmic acceleration is dark energy, a mysterious form of energy that permeates space and resists gravity. Dark energy is thought to make up 73% of the total energy density of the universe. Unlike ordinary matter, which has a gravitational pull, dark energy appears to be a repulsive effect pulling galaxies apart. The nature of dark energy remains one of the most profound enigmas of modern astrophysics, with various theories proposed to describe its properties, including the cosmological constant, which is a constant energy density. Observations supporting cosmic acceleration come primarily from studies of distant supernovae, particularly type Ia supernovae. These supernovae serve as reliable distance indicators, allowing astronomers to measure the expansion history of the universe. When the researchers found that these supernovae were weaker than expected, it showed that they were farther away than previously thought, leading to the conclusion that the expansion of the universe is accelerating rather than accelerating. Another piece of evidence for cosmic acceleration is observations of the cosmic microwave background radiation and large-scale structure. Measurements of changes in the cosmic microwave background after the Big Bang provide insight into the density and composition of the early universe. The subsequent spread of galaxies and galaxy clusters through space is consistent with an accelerated expansion scenario, as structures formed from density fluctuations are influenced by dark energy. Despite extensive research on dark energy and cosmic acceleration, questions remain about its true nature and behavior. Ongoing experiments and observational campaigns aim to improve our understanding, potentially revealing physics and changing our understanding of the evolution and fate of the universe. The implications of cosmic acceleration and dark energy are not only interesting, but also delve into deeper questions about the very fabric of reality. The expansion of the universe is of great importance not only for the regions we can observe, but also for the regions beyond the observable limits. As the universe expands, it affects the dynamics and distribution of matter on large scales, and this expansion drives the evolution of cosmic structures both within our observable universe and in regions beyond it. One of the main effects of this expansion is the notion that the regions beyond our observable universe may be shrinking away from us at speeds exceeding the speed of light due to the metric expansion of space. This means that light from galaxies in these distant regions can never reach us, remaining forever beyond our cosmic horizon. As the universe continues to expand, many of these regions will move away from our observables, leading into the future, when the night sky will slowly empty of distant galaxies. This eventual isolation can lead to a universe that appears dark and desolate, changing our perception of space over cosmological timescales. Magnification effects raise interesting questions about the potential existence of structures beyond our observable universe. While we cannot directly observe these regions, theoretical models suggest that they may contain galaxies, clusters, and cosmic filaments similar to our observable limits. However, these structures evolve differently depending on local conditions, gravitational interactions, and dark energy distribution. Such changes may mean that the universe we see is not just an extension of what we can observe, but may offer unique features. In addition, the rate of expansion can affect the fate of the universe. If the properties of the dark model change, as some models suggest, this could lead to very different cosmic scenarios in the observable and unobservable regions of the universe. For example, if dark energy becomes stronger, it could lead to Big Rip-like scenarios where cosmic structures are disrupted, even affecting the integrity of the farthest reaches of space. Ultimately, as scientists continue to study the fundamental laws governing the expansion of the universe, our understanding of its consequences will be near and far. Uncharted regions of the universe may hold secrets that defy our understanding and help us understand the fabric of reality, even if we never see it with our own eyes. The ultimate fate of the universe is a topic of great intrigue among cosmologists, with prevailing theories suggesting several potential scenarios based on the expansion of the universe and the nature of dark energy. As the universe continues to expand, it will push galaxies further apart. This expansion, driven by dark energy, is accelerating over time, leading to the possibility of a superfreeze. In this scenario, the universe becomes increasingly cold and desolate. Stars run out of fuel and galaxies recede until they fall into obscurity. Alternatively, some models predict a major collision. In this scenario, if the universe is dense enough, gravity can eventually stop expanding. The universe would then collapse back under its own gravity, potentially creating a singular state similar to the conditions at the beginning of the universe. This collapse could return all matter to an infinitely dense point, possibly leading to another Big Bang and the birth of a new universe. Another interesting possibility is the Great Rip. This theory suggests that if dark energy becomes stronger, it can tear apart galaxies, stars, planets, and even atoms. In this case, the fabric of the universe would eventually rupture, causing all structures to collapse violently. Finally, there is the concept of a steady-state universe, in which the expansion continues indefinitely, but the universe does not change over time, filled with new matter continuously created to fill the voids left by the expanding universe. These theories highlight the complexity and uncertainty surrounding the fate of our universe, calling for further exploration and research in the field of cosmology.
In that case, the laws of physics may differ from universe to universe, resulting in drastically different conditions of existence. Exploring the implications of multiple universes of varying sizes expands our understanding of the cosmos and challenges our perception of reality itself. It promotes discussion about the nature of existence, the fine-tuning of physical laws, and the potential for alternative life forms in the larger landscape of the multiverse. The prospect of other universes with dimensions configured in ways we cannot currently imagine fascinates scientists and philosophers alike, inviting further investigation into the very essence of the universe in which we live. Another intriguing idea related to the Big Bang is the theory of cosmic inflation. Proposed in the 1970s, this theory suggests that in a very brief moment, less than a trillionth of a second, the universe underwent an exponential expansion. This rapid inflation helps explain the uniformity of the cosmic microwave background and the large-scale structure of the universe we observe today. By smoothing out any irregularities, inflation solves why the universe looks nearly uniform on a large scale. Some alternative theories have emerged that challenge or seek to extend the Big Bang model. The cyclic model, for example, states that the universe undergoes endless cycles of expansion and contraction, with each cycle leading to a new Big Bang. According to this view, the universe has no ultimate origin or end, but exists in an eternal rhythm of birth and rebirth. This model has intriguing implications for understanding concepts such as time and entropy. Additionally, string theory offers a different perspective, suggesting that our universe is just one of many in a larger space. In this structure, the interaction of fundamental strings can lead to the creation of many universes, each with its own distinctive properties and laws of physics. This multiverse view raises questions about the nature of reality and our place in the vast and potentially infinite cosmos. As scientists continue to explore and collect data, our understanding of the origins of the universe may evolve further, potentially leading to revolutionary ideas that deepen our understanding of existence itself. Each theory, established or new, contributes to the complex tapestry of ideas that shape our quest to unravel the mysteries of the cosmos. Cosmic rebirth theory, often associated with the cyclical model of the universe, suggests that the cosmos undergoes endless cycles of expansion and contraction, leading to a kind of eternal renewal. In this framework, the universe has no single beginning or end, but instead exists in a continuous process, where each cycle begins with an event similar to the Big Bang and ends in a collapse, sometimes called the Big Crunch. In its basic form, the theory suggests that after an expansion phase, the universe eventually reaches its maximum size. At this point, gravitational forces may become dominant, causing the universe to contract. This era of contraction will cause all matter to converge, eventually creating the conditions for a new singularity very similar to the one theorized to have existed during the Big Bang. From this special state, a new expansion can begin, marking the rebirth of the universe in a cycle that can repeat itself endlessly. This concept addresses some intriguing questions in cosmology, such as the nature of time and entropy. In a cyclical model, time would not be linear. Each cycle could reset conditions, potentially recalibrating the entropy of the universe. However, critics point out that during each cycle, the universe's entropy tends to increase, raising concerns about whether the universe will be able to transition smoothly from collapse to new expansion. If the expansion continues, the effects will increase. Stars inside galaxies can feel the strain from this accelerated expansion. Over time, the gravitational forces that keep individual stars together will not be enough to resist the increasing pull of dark energy. Eventually, stars will lose their gravitational pull, causing their structures to collapse. This dramatic expansion will progress even further to affect solar systems and galaxies, tearing apart planets, moons, and other celestial bodies. Eventually, even the atoms and subatomic particles that make up matter can be torn apart, leading to a universe in which all forms of structure disintegrate under the stress of the relentless thrust of dark energy. If the Big Rift unfolds as described, it will culminate in an event where, at some point in the future, all matter in the universe is completely torn apart, reducing it to its most fundamental components. This scenario raises profound questions about the nature and properties of dark energy, prompting scientists to investigate its fundamental role in the cosmos and how it affects the ultimate fate of the universe. As research progresses, the effects of the Big Dipper continue to shape discussions about the long-term evolution of the universe, inviting further exploration of the mysteries of cosmic forces. Boltzmann's brane hypothesis emerges from the field of statistical mechanics, proposing a thought experiment regarding the nature of consciousness and the universe. He argues that, given the vastness and infinite potential of the universe, it is statistically likely that a single brane would spontaneously form in a state of chaos, complete with false memories and representations. This hypothetical brane would arise through random fluctuations in a high-entropy environment. The implications of the Boltzman brain hypothesis are profound and challenge our understanding of reality. If such a brain could exist simply by chance, then it raises questions about the reliability of our own existence and consciousness. The universe we perceive may just be a fleeting, random arrangement of particles, while real existence may be far more chaotic and unstable than we imagine. This thought experiment intersects with cosmology, particularly in discussions of the nature of time and entropy. This means that as the universe continues to expand indefinitely, low-entropy regions may become increasingly rare. This could eventually lead to a scenario where Boltzmann brains become more common than actual conscious observers, fueling philosophical debates about the nature of knowledge and existence. As we consider our place in the cosmos, Boltzmann's brain hypothesis serves as a stark reminder of the complexity and entanglement of the universe. It challenges the notion of reality and pushes us to explore our understanding of consciousness, existence, and the underlying laws that govern everything around us. String theory offers a groundbreaking foundation in physics by suggesting that the fundamental building blocks of the universe are not point particles, but tiny, vibrating strings. One of the most fascinating aspects of string theory is its requirement for additional dimensions beyond the usual 3 dimensions of space and 1 dimension of time. Depending on one's version of string theory, these extra dimensions can range from 6 to 11, greatly expanding the dimensional landscape of our cosmos. Earth is about to get a new guest in its space neighborhood, but this is no ordinary flyby. Imagine a small rock the size of a house circling the Earth for a couple of months before waving goodbye and continuing its journey around the Sun. This is the story of 2024 PT5, a small asteroid that is set to become Earth's temporary mini-moon for about 50 days, starting in late September 2024. In this video, we'll explore what makes this mini-moon so special, delve into the science behind its temporary takeover of Earth, explore the implications of such events for protecting the planet, and see what we can learn from studying these fleeting space visitors. Discovered in August 2024 by the Atlas Asteroid Collision Warning System, 2024 PT5 is a small asteroid about 10 meters in diameter that has been identified as a potential mini-moon for Earth. Atlas is a state-of-the-art automated system designed to detect asteroids that could threaten our planet. Its rapid detection allows astronomers to quickly calculate the asteroid's path and assess potential risks. In the case of 2024 PT5, the analysis revealed the unexpected and encouraging news that this small asteroid is not on a collision course with Earth. Instead, it will be briefly captured by Earth's gravity, turning into a temporary mini-moon. What makes it particularly interesting is its size and trajectory. At only 10 meters across, it is relatively small compared to the larger asteroids that often make headlines. However, it is this small size that makes it more susceptible to temporary capture by Earth's gravity. Unlike larger asteroids, which fly past Earth at high speed and continue their orbit around the Sun, smaller objects like this one can be caught by the gravitational tug-of-war. This tug-of-war results in a temporary capture, creating what is often referred to as a mini-moon. This asteroid probably comes from the Arjuna asteroid group, which consists of small asteroids with orbits around the Sun very similar to Earth's. These asteroids, due to their proximity and orbital patterns, are more likely to fall under the gravitational pull of Earth. Scientists have determined that 2024 PT5 is a natural object, not space debris, which is important because it means that its trajectory is not affected by the forces that affect man-made objects in space, such as solar radiation pressure or atmospheric drag. This natural orbit makes it an ideal candidate for a temporary mini-moon. Understanding the nature of 2024 PT5 is critical for several reasons. First, it provides a rare opportunity to closely study a near-Earth object, even if only for a short period. Second, such events serve as valuable test cases for improving our asteroid detection and tracking systems. When we talk about Earth capturing an asteroid, we're really talking about a delicate balance of power. In particular, the gravitational attraction of the Earth and the Moon combined with the speed of the asteroid itself. One possibility is that the geometry of higher dimensions may affect the behavior of gravitational waves. These waves, caused by catastrophic cosmic events such as black hole mergers, crisscross the fabric of space-time. If there are additional dimensions, they can provide new paths for these waves, affecting their propagation and detection. This could improve our understanding of cosmic events and enhance our ability to observe phenomena that were previously unavailable. Given the expansion of the universe, these extra dimensions could also change our understanding of dark energy, the mysterious force driving the universe's accelerated expansion. If higher dimensions interact with known forces in unexpected ways, this could lead to different effects on the rate of cosmic expansion and potentially shed light on the nature of dark energy itself. By exploring how these extra dimensions connect to our own, scientists could find ways to explain the accelerating expansion of the universe. In addition, higher dimensions can affect fundamental particle properties, contributing to variations in particle behavior at extremely high energies, such as in cosmic rays or particle accelerators. These effects may shed light on the unification of fundamental forces of nature, providing a path to a more comprehensive theory of physics. Ultimately, exploring the implications of higher dimensions encourages a re-evaluation of our understanding of the universe, opening the door to new theories and vast possibilities. The concept of compact dimensions arises in string theory and other higher dimensional theories, where additional spatial dimensions beyond the familiar three exist, but are not as easily observed. These dimensions are said to be compacted, meaning they are compacted into extremely small, intricate shapes that are often described mathematically as polymorphic structures. Because they are very tiny, typically on the Planck scale, they remain undetected by modern experimental techniques that probe only subatomic scales. The existence of compact dimensions has significant implications for how we understand the fundamental forces of nature and the particles that make up the universe. In this framework, the specific topology or shape of compacted dimensions affects particle properties such as mass and charge. Different compactifications can lead to different physical scenarios, potentially explaining why some particles appear in our universe and others do not. Each unique compaction has its own set of fundamental particles and interactions, suggesting that the characteristics of our universe may be shaped by the way these extra dimensions are configured. Moreover, compact dimensions may also play a role in determining the fundamental constants that govern the universe. Because these measurements can produce a variety of physical landscapes, they can contribute to the so-called landscape problem in string theory, in which there are a large number of combinations, each leading to different physical laws. This raises interesting questions about the anthropic principle and why our universe seems fine-tuned for life. Could it be that we are simply in one of the many possible configurations of compacted dimensions that allow for such a diverse range of physical phenomena? Finally, when the compact dimensions interact with known forces, it can provide new physical predictions. For example, gravitational interactions can extend to these hidden dimensions, changing our perception of phenomena such as gravity and its behavior at different scales. The study of compact dimensions continues to pose intriguing challenges, pushing the boundaries of our knowledge and offering a window into the mysteries that govern the fundamental structure of reality. Gravity in higher dimensions operates according to principles that may differ significantly from our familiar three-dimensional understanding. In the context of general relativity, gravity is described as the curvature of spacetime caused by mass and energy. When we extend this framework to higher dimensional space, gravity not only affects the three spatial dimensions we perceive, but also interacts with additional dimensions, creating fascinating complexities. In higher dimensional theories, such as string theories, the presence of extra dimensions can change the behavior of the gravitational force. For example, gravity may be much weaker in higher dimensions than in lower dimensions. This is because in a five-dimensional scenario, gravity can spread out more, reducing its strength. This characteristic may help explain why gravity is much weaker compared to other fundamental forces such as electromagnetism, potentially providing insight into the hierarchy problem in particle physics. Moreover, the geometry of the extra dimensions can affect gravitational waves, which are ripples in space-time generated by the acceleration of masses. Like any wave traveling through a medium, gravitational waves can cut through these higher dimensional spaces in unique ways, resulting in different propagation and interaction characteristics. Such effects could become observable in experiments designed to detect gravitational waves, providing a potential means of studying the nature of higher dimensions. Additionally, gravitational interactions with compacted dimensions can lead to phenomena such as gravitational leakage into these hidden dimensions. This may explain why we perceive gravity differently than other forces, and may also have implications for the dynamics of our universe. Theoretical studies of these complex interactions not only challenge our current understanding of gravity, but also reveal ways to unify nature's fundamental forces, illuminating the intricate web that connects the universe's dimensions. The concept of multiple universes existing in different dimensional configurations is a fascinating idea that stems from theories such as string theory and the multiverse hypothesis. In this framework, it is assumed that universes can arise from different mechanisms or compactifications of higher dimensions, resulting in an almost infinite variety of physical realities, each with its own set of laws and constants. These alternate universes may have their own properties, initial conditions, and even different forms of matter and energy. Each universe may exhibit certain dimensional characteristics that will affect fundamental forces and particle behavior. For example, in a universe with more compacted dimensions, the interactions between particles may be very different from the interactions in our familiar three-dimensional space. This variability opens up a wide range of possibilities, where some universes may allow complex structures and life, while others may lead to completely different physical phenomena, potentially producing unrecognizable forms. The idea of distinct dimensional configurations also raises philosophical and scientific questions about the nature of reality. If these universes coexist, they may be completely separate and isolated, making them impossible to detect. This is consistent with the multiverse interpretation of quantum mechanics, suggesting that each quantum solution branches out to create different realities in a vast multiverse. Various versions of the theory of cosmic rebirth have been proposed to solve these problems. Some versions offer additional mechanisms to counteract the increase in entropy, combining complex ideas from quantum mechanics and string theory to specify how each cycle can occur. Moreover, these models emphasize the possibility of new physical processes or phenomena occurring with each cycle, which may lead to different physical laws or states in the reborn universe. As our observational tools and theoretical framework develop, researchers are cautiously exploring the implications of cosmic rebirth. While the notion of an eternal universe challenges traditional understandings of beginnings and ends, it opens exciting avenues for further investigation into the very nature of existence, time, and the structure of reality itself. The Big Freeze is one of the leading theories about the ultimate fate of the universe, based on the observation that the universe is expanding at an increasing rate. This concept is also closely related to the behavior of dark energy, the mysterious force that drives the acceleration. In this scenario, As the universe continues to expand, galaxies will gradually drift apart over vast stretches of time, cooling and transforming the cosmic landscape. As the stars expand, they will begin to exhaust their nuclear fuel. In 1 to 2 trillion years, most of the stars will have burned out, leading to a universe filled mostly with white dwarfs, neutron stars, and black holes. The stellar objects that remain will be dimmer and hotter at first, but eventually fade into cold remnants. Over an incredibly long period of time, the light and energy produced during star formation will have greatly diminished, leaving the universe in a dark, cold state. During the Big Freeze, the temperature of the universe will approach absolute zero as the galaxies recede into the vast void of space. Quantum fluctuations may still cause random interactions, but the overall space environment will become increasingly desolate. This final state, characterized by the absence of significant energy sources, means that life as we know it will become impossible, and any remnants of systems that were once active will undergo further degradation. The Big Freeze is a scenario devoid of significant physical activity, representing a universe that becomes cold and lifeless. Although far from over, studying the Big Freeze adds depth to our understanding of the long-term evolution of the cosmos and forces us to grapple with profound questions about the existence and nature of time. As more data is collected and our understanding of dark energy improves, the scientific discourse surrounding various end-of-the-universe scenarios, including the Big Freeze, will continue to evolve. The Big Bang scenario is a hypothetical outcome of the end of the universe, based on the assumption that dark energy continues to accelerate the expansion of the universe at ever-increasing rates. If the effects of dark energy increase over time, this scenario suggests that the repulsive force of dark energy may eventually overcome all forms of gravitational attraction. Initially, the galaxies will continue to move away from each other, similar to the Big Freeze scenario, but the rate of expansion will accelerate even more. As dark energy builds up, it will begin to affect the structures of the galaxies themselves, causing them to move away at ever-increasing speeds. At some point, the gravitational bonds that hold galaxies together will weaken, causing disruptions in galaxy clusters. For this mini-moon, the conditions are just right for it to be captured by Earth's gravity for a short period, making one complete revolution around the planet in 50 days. When such an asteroid approaches Earth, it enters a region of space where the gravitational attraction of our planet begins to dominate that of the Sun. If the asteroid's speed and trajectory match perfectly, it can enter a temporary orbit around the Earth. However, unlike our permanent moon, which is in a stable orbit, these mini-moons are often in highly elliptical orbits, and their existence is fleeting. Current predictions for 2024 PT5 suggest that it will be captured by Earth's gravity in late September 2024, complete a single orbit around our planet, and then return to its orbit around the Sun by mid-November. The phenomenon of mini-moons, although relatively rare, has been observed several times, each of which has provided unique insight into the nature of small near-Earth objects and their interaction with our planet's gravity. One of the most well-documented cases was 2006 RH-120, a small asteroid that orbited Earth from 2006 to 2007. This mini-moon had a diameter of 3 to 6 meters and was in the sphere of gravitational influence of the Earth for about a year. This was an important event because it was one of the first times that astronomers were able to track the orbit of such a small object in real time, giving them unprecedented insight into the dynamics. Another notable example is 2020 CD3, which was discovered in 2018 and remained in orbit around Earth until 2020. This mini-moon was slightly larger than the 2006 RH-120 and was estimated to be about 1 to 2 meters in diameter. Its capture provided valuable data that helped refine models of how small objects interact with Earth's gravity. These past occurrences of multiple satellites have contributed significantly to our understanding of near-Earth objects. They showed that Earth's gravity can temporarily capture small asteroids, causing them to orbit briefly before continuing their journey around the Sun. This process is critical to understanding the potential risks associated with near-Earth objects, as it highlights the dynamic nature of these small bodies and their potential to approach Earth closer than originally predicted. Moreover, these studies allow us to look into the possibilities of future research and use of near-Earth objects. Mini-moons, like 2024 P-T5, provide a unique opportunity for future space missions to study these small bodies up close, offering insights into their composition, structure, and potential resources. A better understanding of mini-moons could also help in planning missions aimed at mining valuable materials on asteroids or even in developing new technologies to deflect asteroids and protect the planet. Thanks for viewing. As we continue to explore and study these fleeting visitors, we are unlocking new mysteries of our cosmic neighborhood and developing better tools to protect our planet from potential threats. The story of 2024 PT5 is a reminder of the dynamic and ever-changing nature of our universe. The dominant theory of the origin of the universe is the Big Bang theory, which suggests that the universe began as an infinitely hot and dense singularity approximately 13.8 billion years ago. According to this theory, there was a rapid expansion that initiated the cooling process and allowed the fundamental particles to form. This expansion is still ongoing, and today we observe it as the red shift of distant galaxies. The cosmic microwave background, the faint afterglow of this early expansion, provides a key piece of evidence, providing a snapshot of the universe roughly 380,000 years after the Big Bang. The implications of these additional dimensions are both profound and staggering. These sizes are considered compacted, which means they are packed so tightly that they are invisible on conventional measurement scales. However, their existence could fundamentally change the laws of physics as we understand them. For example, the properties of fundamental particles, including mass and charge, can be affected by the shape and size of these hidden dimensions. As such, they may hold the key to unifying all fundamental forces, including gravity, within a single theoretical framework. Moreover, the existence of extra dimensions can open up explanations of unresolved questions in physics. For example, they could offer insights into the nature of dark matter and dark energy, the mysterious components that make up most of the mass energy of the universe but remain poorly understood. The interactions that occur in these extra dimensions can provide the missing pieces to our understanding of how the universe behaves on both large and small scales. Finally, exploring the implications of string theory's extra dimensions opens up imaginative possibilities, such as the existence of parallel universes or alternate realities. It has plagued scientists and philosophers, inspiring us to rethink our concepts of reality and existence. Delving into these extra dimensions could revolutionize not only our understanding of physics, but our understanding of the universe in which we live. Higher dimensions, theories such as string theory suggest, can have a profound effect on the very structure of the universe and its large-scale structure. In a typical three-dimensional space, gravitational and electromagnetic forces operate within a limited framework. However, with additional dimensions, the interaction of these forces can undergo significant changes, which can lead to new forms of matter and energy. These dimensions can influence additional gravitational interactions that affect the formation and evolution of celestial bodies such as stars, galaxies, and clusters.